Hello, this is the lecture for inverse functions. An inverse function is one that undoes or reverses another function. So mathematically, if we have a function called f and a function called g, we would say they are inverses if, when we compose g into f, we get back to the original input. Or when we evaluate f of g of x, we end up with x. And the reverse composition is also true. G of f of x would also have to be equal to x. Or when we compose the function f into g, we'll get back to that original input. Okay? The notation that we use typically to refer to inverse functions is this f with a -1 up there where the exponent might be f -1 of x. But in this case, the -1 does not mean it's an exponent. It's just a notation when we're dealing with functions just to refer to an inverse function. All right, let's look at some examples. In these first three examples, we want to determine whether or not these pairs of functions are inverses of each other. They're going to be inverses of each other, or one will undo the other one, or reverse the other function, if, when we compose them and simplify, they simplify out to the original input, or x. So if we wanted to know if f of x and g of x are inverse functions, we would need to find f of g of x. Let's compose g of x into f. So f of g of x, is going to be 2 times, instead of x, we want g of x plus 8 over 2, and then minus that 8. All right, when we simplify this, look at this, the 2's divide out, so we have x plus 8 minus 8, and the 8's add out, so this simplifies right down to x. Right? By the definition, if f of g of x equals x, then they are inverses. So I think it's yes. Hey, let's go the other way and make sure. Let's find g of f of x and make sure that that also evaluates to x. G of f of x is going to be, instead of x plus 8, it's going to be 2x minus 8. That's our f. And plus that 8 over 2. Well, these 8's are going to add out, and we'll have 2x over 2, and then those 2's divide out, so that also simplifies down just to x. Right? So, since f of g of x equals x, and g of f of x equals x, or when we compose g into f, we get back to the original input. When we compose f into g, we get back to the original input. We would have to say that yes, this pair of functions, these two functions, are inverses of each other. Let's look at the next example. J of x is 2x plus 4. K of x is x over 2 minus 4. Well, at first glance, it kind of looks like maybe those are inverses too, but we better not jump to a conclusion. Let's go ahead and compose, let's do k of x into j of x. Let's find j of k, oops, that's a k, j of k of x. All right, let's find j of k of x. What is that, j of k of x? Let's see, that's going to be 2 times, and then k of x is x plus 2 minus 4. And I've also got this plus 4. It's really tempting to add out those 4's, isn't it? That's not what order of operations tells us to do, right? Order of operation tells us that we need to first distribute that 2 before we can start combining like terms. All right, let's distribute that 2 then. So we get 2x over 2 And then 2 times negative 4 is minus 8. And then we've got that plus 4 out there at the end. Well, these 2's are going to divide out, but look at this. Negative 8 plus 4 is negative 4. So this simplifies down to x minus 4, not x, right? This x minus 4 is not equal to x, not. So we have to say no. These are not inverse functions. I don't even need to evaluate it the other way. If it doesn't evaluate one way to x, if it doesn't simplify down to x, then when we compose the other direction, it's also not going to simplify down to x. One more example. The square root of x minus 6 and x plus 6 squared. At a first glance, it looks like those might be inverse functions, right? Let's compose them and find out for sure. All right, so we'll find, let's just find m of n of x first. Okay, m of n of x is going to be the square root of x, which was going to be n of x, so x plus 6 squared, then minus 6. All right, we can't just divide out those 6, or I'm sorry, add out those 6's though, because look, I have to square x plus 6. This is the square root of x plus 6 times x plus 6 minus 6, right? Which is the square root of, let's see, x times x is x squared plus 6x and another 6x, so that's plus 12x plus 36, then minus that 6. So this simplifies down to the square root of x squared plus 12x minus, I'm sorry, plus 30. And that is not the square root of x plus 6 squared. That, in fact, doesn't even simplify any further. So this is not equal to x. So once again, no, these are not inverse functions. So be very careful. At first glance, functions can look like inverses, but you must compose one function into the other function before you can be certain that two functions are inverses of each other. Now let's talk for a minute about the graphs of inverse functions. Okay, we know that an inverse function reverses another function, or undoes, if you will, another function. When we're looking at the graphs of inverse functions, we have to keep in mind not all functions have inverses, right? If a function passes the horizontal line test, or if it's a one-to-one function, okay, here's the horizontal line test. If it's a one-to-one function, that means it's one-to-one. If it's a one-to-one function, then it will have an inverse, okay? If it's not one-to-one, if it does not pass that horizontal line test, let's look at this function f here. Here he is, this is f, the function f. It does pass the horizontal line test. Any horizontal line that I can imagine, anywhere is only going to intersect that graph in one place. Even right here, it looks like it might, but it doesn't. It only intersects it in one place. So that function up there does have an inverse. The inverse graph, the graph of an inverse function, is going to be a reflection about the line y equal x. So if I were to put the line y equal x in here, it'd be right here. That's the line y equal x. And we can see that these two graphs, f and f negative 1, we'll make that one pink. But this is f negative 1. The yellow one is f. We can see that they are reflections or about the line y equal x, or that they're symmetric to that line y equal x. Okay? So if we wanted to sketch the graph of an inverse function, all we would need to do is sketch the line y equal x and then reflect it, right? Well, sometimes that's easier said than done, isn't it? Let's see, here's my line, y equal x, and this function over here is my original function. We'll call him my f, right? We'll let him be f. Okay, f negative 1, it's going to be a reflection across this line, or symmetric to this line, y equals x. Well, this point here looks like I can imagine where that reflection is going to go. It's going to be here. It's an open circle, actually. It's going to be here, but these get a little bit harder, don't they? It's going to be somewhere over here, somewhere over here. I can kind of get an idea what it's going to look like. But if I want to know for sure, I should do this. This point here, that open circle point that reflects over to that pink point I just drew, it has the coordinates 0, -1. Okay, x is 0, y is -1. The reflected point over here has the coordinates, look, -1, 0. So the graph that's symmetric to f, the f -1 graph, we're going to put him over here in pink, that f -1 graph, the inverse of f, that inverse is going to have points on it that have the x's and y's switched. Look, here we had x was 0, y was -1. On the reflected point, we have x is -1 and y is 0. All right. So because of that, I want to make sure that I identify some clear points on my original graph before I sketch its inverse. All right, here's a clear point on f. It's got the coordinates 5, 0. All right, that means the point with the coordinates 0, 5 is going to be on the inverse. That would be this point right up here. We switch our x's and our y's. That also means that the point here with the coordinates -1, -5, the reflected point, or a corresponding point on the inverse of this function, is going to have the coordinates -5, -1. I probably didn't put that label real well, but that's okay. So -5, -1, it's right in the middle where I put that label, right there. That's fine. And then this last point down here, this one has the coordinates -2, -6. So that means -6, -2 is going to be over here on the inverse. That's that point right there. Okay. If I connect these points, then I can see there's my graph in pink of f -1. It's symmetric to this line y equals x. Can we do another example? Let's look at this one here. Let's put our y equals x line in that we want to be symmetric to. I don't know about you, but I don't think I can really visually just see where these reflected points are going to be. I think I want to label them and then switch the x and y coordinates. Let's see, this point down here is going to be 5, -2. This open circle point here is going to be 3, -1. Okay, this point up here is going to be 2, 3. And over here we got -2, 4. Okay, so if I want to plot the reflections, I want to switch my x and y coordinates. Okay, so 5, -2 becomes -2, 5 right here. 3, -1 becomes -1, 3 right here. 2, 3 becomes, oh, I did that wrong, didn't I? -2, 5, no, that's right. -1, 3. Okay, so 2, 3 becomes 3, 2 here. And then -2, 4 becomes 4, -2 here. All right, so this one is a little bit trickier. I definitely could not have done that visually. I definitely needed to identify the coordinates and the points. Okay. All right, so graphs of inverses are a reflection across the line y equals x of the function. Okay, so let's take a look at inverses when we consider them represented as a table of values. Okay, we saw when we were graphing inverse functions that the x and y coordinates switched between the function and its inverse. Well, the same thing happens here when we look at a table of values. Here we have a table of values. We have x, the input, and then we have f of x, the output, or sometimes f of x is referred to as the y, right? The output of that function f. So if we want to find f of 1, that's not too hard to do, right? We're just going to evaluate that function f when x is 1. When x is 1, f of x is 5. So that's not too hard to do. Okay. Now, if we wanted to find what x is when f of x equals 0, all right, what are we doing there? F of x equals 0, that means the y equals 0. When f of x is 0, what is x going to be? Well, we need to look in the f of x column. We need to find when it's 0. There it is. When f of x is 0, x then is equal to 6. Okay, that's not too bad, but now we start thinking about the inverse function, all right? So we've got to be very careful here. Think about the definition of the inverse function, right? Here we want to find the inverse of f of 5, right? The inverse of f of 5, right? So what is this saying here? Is this saying find f of 5? No. It's saying find the inverse of f of 5. So what does that mean? That means f negative 1 of 5, or the inverse of f of 5. That's actually saying that the x is 5. That's actually saying that the x is 5. So when the x is 5, what is the y going to be? 3. Okay. If the inverse of x is 6, okay, what is that saying here? Then what is x going to be? Well, if the inverse of f of x is 6, then what is this x input to f negative 1 going to be? This is very confusing, right? So what we're saying here actually is the inverse is the x, right? The inverse here is the x. That's the x. It's 6. Okay. So at 6, that maps us to 0 here, right? So then does x going to be equal 0? Well, let's think about that. Does that make sense? We're switching our x's and y's here, right? We're switching our x's and y's. If y is 0, x is 6. If x is 6, y is 0. Even though it says x equals 0, it's the input to the inverse here. It's the input to the inverse here. So we have to be really, really, really careful with that, right? We have to be really, really, really careful with that. All right. Now let's take a look at finding inverses from functions. All right, if we have a function in its function notation, to find the inverse, we've just discovered that on the inverse of a function, the x's become y's and the y's become x's. So to find the algebraic representation or the function notation of the inverse of a function, what we want to do is first rewrite that function as an equation, right? Substitute y in for your f of x. Then switch your x's and y's, okay, because the graphs are symmetric across that line, y equal x. Then go ahead and solve for y. And then when we're all done, if we're looking for an inverse, we need to specify it as an inverse. All right, let's take a look at some examples of that. If f of x equals 5x plus 8, let's see if we can find the inverse f negative 1 of x. All right, our step 1, right, said write it as an equation. So we'll say y equals 5x plus 8, and then we're going to switch our x's and y's. Okay, so that was our step 1. Our step 2, switch our x's and y's. So x equals 5y plus 8. All right, now in our step 3, we're going to solve for y. Okay, we're going to solve for y. So let's see, we'll subtract that 8 from both sides. So we'll say 5y equals x minus 8, and then we'll divide everything by 5. Okay, so y then equals, we'll just say 1/5 x minus 8/5. Okay, and then our fourth step, we were looking for an inverse. Right now, that's an equation. We want to write it as an inverse. So we want to say f-1 of x is going to equal 1/5 x minus 8/5. Okay, look at this next one. G of x is the cubed root of x plus 9. All right, let's write it as an equation first. So y equals the cubed root of x plus 9. Now let's switch the x's and y's. X equals the cubed root of y plus 9. Okay, now to solve for y, it's under a cube root, so we're going to need to cube both sides. So we'll say x cubed is going to equal y plus 9. Okay, now we solve for y. Y then, we just subtract that 9 from both sides. So y is going to equal x cubed minus 9. Now let's write that as an inverse function. f-1, oh no, it's g, sorry. G -1 of x equals x cubed minus 9. Okay, there's one that's a rational expression. These can be a little tricky, right? Let's do that one. Let's write this first as an equation. Y equals 15 over x plus 7. Now let's switch our x's and y's. X equals 15 over y plus 7. Okay, now we need to solve for y. How do we do that? We got to get y out of the denominator. So let's just multiply both sides by that whole denominator. Multiply both sides by y plus 7. All right, and these will divide out. So then we get x times y plus 7 equals 15. Here. Let's distribute that x. So x, y plus 7x equals 15. We're still solving for y, so we need that term by itself. Let's subtract the 7x from both sides. Okay, so then xy equals 15 minus 7x. And then we don't want x, I want y, so we're going to divide everything by x. So y then is equal to 15 over x minus 7. Lastly, as in function notation, f-1 of x is 15 over x minus 7. Okay, we'll do one last example. Write it as an equation, y equals 9x cubed minus 7. Switch your x's and y's. So then x equals 9y cubed minus 7. Solving for y, so add that 7 to both sides. I'll go back over here. So then 9y cubed equals x plus 7, and divide by 9. So now y cubed equals x plus 7 over 9. And we'll need to take the cubed root of both sides to get just y. Y then equals the cubed root of x plus 7 over 9. Lastly, in function notation, f-1 of x equals the cubed root of x plus 7 over 9. Okay. And that ends the lecture on inverse functions.